In episode 114, titled Recommenders, Similarity, Collaborative Filtering, and ALS in Plain Terms, we focus on recommender systems as business tools that must match the goal you actually care about, not just the data you happen to have. Recommenders are often discussed as if they are one technique, but they are really a family of approaches that differ in what signals they use and what assumptions they make about why people choose items. The exam expects you to recognize the major families, understand the cold start problem, and be able to explain matrix factorization and alternating least squares in clear, non-mathematical language. In practice, the right recommender depends on whether you need personalization, whether you have rich item metadata, and whether you can collect enough user interaction behavior to learn patterns. It also depends on constraints like real-time serving versus batch generation, and on governance concerns like bias and feedback loops. The goal of this episode is to make recommender concepts feel like practical engineering choices rather than like specialized jargon. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Content-based recommendation uses item attributes to recommend items similar to what a user has already liked or interacted with. The core idea is to represent items using their features, such as category, description text, tags, price range, or other metadata, then measure similarity among items in that feature space. If a user engaged with certain items, the system recommends other items that are close in attribute space, essentially saying, here are more items like the ones you already showed interest in. This approach is especially useful when you have strong item descriptions and when you want recommendations to be explainable, because you can often point to shared attributes as the reason for a suggestion. Content-based systems also handle new items better than purely behavior-based systems because a new item can be represented by its attributes immediately, even before it has interaction history. The trade is that content-based methods may struggle to capture unexpected tastes because they recommend within the neighborhood of known attributes rather than discovering hidden associations across different kinds of items. In plain terms, content-based recommenders recommend by similarity of item descriptions rather than by similarity of user behavior. Collaborative filtering uses user behavior patterns and interactions rather than item attributes, meaning it learns from what users do instead of what items are. The key assumption is that users who behave similarly will tend to like similar items, and items that attract similar users are related in a meaningful way, even if their attributes differ. In collaborative filtering, the system uses interaction histories such as clicks, views, purchases, or ratings to discover patterns like users who engaged with these items also engaged with those items. This can produce powerful recommendations because it can uncover relationships that are not obvious from content alone, such as cross-genre media preferences or complementary retail purchases. Collaborative filtering can also adapt as tastes shift because it learns from ongoing behavior rather than from static item descriptions. The trade is that it depends heavily on having enough interaction data, and it struggles with cold start because it cannot learn behavior patterns for new users or new items with no history. In plain terms, collaborative filtering recommends based on collective behavior, not on item descriptions. Matrix factorization is a common collaborative filtering approach that learns latent preferences for users and latent traits for items, capturing structure in a user-item interaction matrix. The interaction matrix has users as rows and items as columns, with entries representing ratings or other interaction signals, and it is usually sparse because most users interact with only a small subset of items. Matrix factorization approximates this sparse matrix as the product of two lower-dimensional matrices, one representing each user as a vector of latent factors and one representing each item as a vector of latent factors. These latent factors can be thought of as hidden dimensions of taste and item characteristics that the system learns automatically, such as a preference for certain styles, difficulty levels, or themes, even if those dimensions are not explicitly labeled. Once you have these vectors, you can estimate a user's affinity for an item by taking a similarity style score between the user vector and the item vector. This produces recommendations that generalize beyond observed interactions because the latent factor space fills in a smooth structure. The practical intuition is that matrix factorization discovers a shared embedding space where users and items can be matched efficiently. Alternating least squares, abbreviated as ALS, is a practical way to train matrix factorization models by updating user factors and item factors in alternating steps. The idea is to treat one set of factors as fixed while solving for the other set, then switch and repeat. First, you hold the item vectors fixed and compute the best user vectors that fit the observed interactions under a least squares style objective with regularization. Then, you hold the user vectors fixed and compute the best item vectors under the same objective, again with regularization. By alternating back and forth, the system gradually improves both sets of factors until the reconstruction of observed interactions is as good as possible under the model. This alternating strategy works well because each subproblem is easier when the other side is fixed, making training more stable and scalable than trying to solve everything at once. ALS is widely used in large-scale recommendation settings because it can handle sparse matrices efficiently and can be parallelized. In plain terms, ALS trains latent factors by taking turns adjusting users and items until they agree with the interaction data. Cold start is a major challenge in recommenders because new users and new items do not have enough interaction data for behavior-based methods to learn from. For a new user, the system may know nothing about preferences, so collaborative filtering has no basis for personalization beyond broad population trends. For a new item, the system may have no interactions, so it cannot place the item in the behavior-learned latent space reliably. Content-based methods mitigate cold start for items because item attributes are available immediately, allowing similarity to other items to be computed. For users, cold start is often addressed by using onboarding signals, early session behavior, or contextual features that provide initial hints, but it remains a practical limitation. Cold start is not a minor edge case because many businesses constantly introduce new products and constantly acquire new users. This is why hybrid approaches are common, blending content and behavior to reduce cold start pain. The exam expects you to recognize cold start as a core recommender problem rather than as a rare inconvenience. Popularity baselines are often used when data are sparse or new because recommending broadly popular items can be a strong default that avoids poor personalization when evidence is weak. A popularity baseline might recommend trending items, top sellers, or widely consumed content, providing reasonable suggestions without pretending to know a new user's preferences. This is not a defeat because baseline recommendations can deliver value immediately and provide a stable fallback when personalization is uncertain. Popularity baselines also help with evaluation because they provide a reference point that more complex recommenders must beat to justify their complexity. In practice, many systems blend popularity with personalization, using popular items as safe options while gradually shifting toward individualized recommendations as more data arrives. The risk of relying too heavily on popularity is that it can create feedback loops that reinforce popular items and suppress discovery, which connects directly to fairness and diversity concerns. Still, as a cold start strategy, popularity is often the simplest workable default. Choosing an approach depends on the scenario, and practicing across media, retail, and learning content makes the selection logic clear. In media recommendations, user behavior is often rich and frequent, so collaborative filtering and matrix factorization can perform well because there is enough interaction signal to learn preferences and similarities. In retail, purchases may be less frequent, but co-purchase patterns can still support collaborative filtering, and content attributes like category and price can support content-based recommendations, especially for new products. In learning content, such as courses or lessons, content attributes like topic, difficulty, and prerequisites can be strong signals, and behavior can reflect learning paths and progression, suggesting that hybrid approaches can be useful. The best choice is driven by what data you can reliably collect and what the business goal is, such as discovery versus retention versus conversion. If you need explainable recommendations for compliance or pedagogy, content-based methods may be favored because reasons can be tied to attributes. If you need high personalization and have ample behavior data, collaborative methods often deliver stronger personalization. Practicing these mappings helps you answer exam questions that present different domain constraints. Implicit feedback requires special handling because clicks and views are not the same as explicit ratings, and their meaning depends on context and exposure. A click may indicate interest, but it may also reflect curiosity, accidental selection, or the effect of where an item was placed on the screen. Views may indicate exposure rather than preference, and absence of interaction may mean the user never saw the item, not that they disliked it. This creates a challenge because many interaction matrices are filled with missing values that are ambiguous, not true negatives. Implicit feedback methods often treat observed interactions as positive signals and unobserved interactions as unknown rather than as negative, sometimes using confidence weights to reflect how strong the signal is. ALS has variants that handle implicit feedback by modeling confidence in observed interactions, which is why it appears often in practice. The exam expects you to recognize that implicit signals require different treatment than explicit ratings because the data semantics differ. Treating clicks as perfect labels is a common mistake that leads to misleading evaluation and biased models. Evaluating recommenders should focus on ranking quality and user outcomes, not simple accuracy, because the goal is to present useful ranked lists rather than to predict a single label. Ranking quality measures whether relevant items are placed near the top of the list where users will see them, and user outcomes measure whether the recommendations lead to engagement, conversion, retention, or other business goals. Accuracy style metrics are often inappropriate because recommendation is not usually a binary classification problem with a single correct answer. It is a ranking and choice support problem. Practical evaluation also must consider exposure bias because you only observe feedback for items that were shown, and this can distort offline metrics. Online evaluation, such as controlled experiments, is often necessary to confirm that improvements in offline ranking metrics translate into real user value. The exam angle is that recommender evaluation is about ranking and outcomes, not about raw classification correctness. Remembering this prevents you from applying the wrong evaluation lens. Bias and feedback loops are major risks because recommenders can reinforce existing popularity and reduce diversity, creating a self-reinforcing cycle that amplifies what is already common. If an item is recommended more often, it gets more exposure, which can lead to more clicks, which makes it appear even more popular, causing it to be recommended even more. This feedback loop can crowd out new items and niche content, which can harm long-term user satisfaction and fairness goals. Collaborative filtering can be especially prone to this because it learns from observed behavior, which is already shaped by past recommendations and exposure patterns. Managing this requires deliberate design choices, such as mixing exploration with exploitation, promoting diversity, or adjusting ranking objectives to account for novelty. Bias also includes demographic and representational bias, where recommendation patterns differ across subgroups due to historical behavior differences and unequal exposure. Communicating these risks is part of responsible governance because recommender systems shape what users see and therefore shape behavior. The exam expects you to recognize feedback loops as an operational risk, not just a theoretical concern. Deployment planning matters because recommenders can be served in batch mode, generating recommendations periodically, or in real time, generating personalized results on demand, and these modes impose different constraints. Batch recommendations are easier to compute and can leverage heavy models, but they may be less responsive to recent behavior changes. Real-time personalization can react to immediate signals, but it requires low-latency inference and efficient retrieval of candidate items, which can constrain model complexity. Many practical systems use a hybrid approach, such as batch-generating candidate sets and then re-ranking in real time with lightweight models based on current context. This architecture choice affects what recommender method is feasible, because a dense matrix factorization score can be computed quickly if vectors are stored, while more complex models may be too heavy for real-time use. Deployment also includes monitoring and updates because recommendations can drift as catalogs change and user behavior evolves. Thinking about batch versus real-time constraints is therefore part of choosing the right recommender family, not an afterthought. The anchor memory for episode 114 is that content uses attributes, collaborative uses behavior, and ALS learns factors. Content-based recommenders start from item descriptions and similarity in feature space, which supports explainability and cold start for items. Collaborative filtering starts from user interaction patterns, which supports discovery of hidden associations and strong personalization when behavior data is rich. ALS is a practical training method for matrix factorization, learning latent user and item vectors by alternating updates until the interaction matrix is well approximated. This anchor gives you a quick mapping that resolves many exam questions about which recommender approach fits which scenario. It also implies the common trade-offs, such as cold start for collaborative and limited novelty for content-based. Remembering this anchor helps you answer quickly while still giving you a path to justify your choice in plain terms. To conclude episode 114, titled Recommenders, Similarity, Collaborative Filtering, and ALS in Plain Terms, pick one recommender type and state its primary risk so your reasoning remains balanced. If you choose collaborative filtering with matrix factorization trained by ALS for a media platform with abundant user interaction data, the primary risk is feedback loops and bias because the model learns from exposure-shaped behavior and can reinforce popularity unfairly. If you choose content-based recommendation for a retail catalog with rich product attributes and frequent new item introductions, the primary risk is limited discovery because recommendations may stay close to known attributes and miss cross-category associations that behavior-based methods could find. In either case, cold start must be addressed explicitly, either through content features for new items, popularity baselines for new users, or hybrid strategies that blend signals. Stating the type and the risk together demonstrates you understand recommenders as decision systems with trade-offs, not as purely technical models. That is the exam-level competence this topic is designed to test. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.